All right, so there's not much to talk about for today. So I'm just going to be talking about vector spaces and then also subspaces. So I'll start by talking about what a vector space is. And this is actually something that you don't need to really know too well, at least not for the linear algebra class being taught at UT Dallas. So I'm not going to spend too much time talking about vector spaces, but I'll just give you guys an idea of what they are. And also I'll note some examples of vector spaces as well. So up until this point, we've been working with vectors in Rn. So if you remember Rn, this was the collection of vectors with n components, x1, x2, and so forth, down to xn. All right. So we've been working with vectors in Rn up until this point, and we've learned how to do certain operations on these vectors. The two sort of most fundamental operations that we have on vectors are vector addition and scalar multiplication. So in particular, we can add these vectors. We can also multiply them by a scalar. We did have some other operations, in particular the dot product. But however, for vector spaces in general, we focus more on just the vector addition and the scalar multiplication. All right. Now, in addition to vectors in Rn, there are other things that we can add and multiply by a scalar. And so some examples. Another item that we've studied in this class are matrices. So we know how to add two matrices together. And we also know how to take a matrix and multiply it by a scalar. We haven't necessarily done too much in this class, but say like in calculus, you certainly talked about like how to add functions together, as well as multiply them by a scalar. So if you have two functions f and g, their sum f plus g would be the function that simply takes x and returns f of x plus g of x. And likewise for scalar multiplication, multiplying a function f by a scalar c just results in a function that multiplies all the outputs of f by c. Okay. And one particular class of functions that we'll be working a little bit with is polynomials. So we've learned how to add polynomials together. We also know how to multiply a polynomial by a scalar. All right, so today I'm just going to be talking a little bit about vector spaces, and I'll probably spend the majority of my time talking about subspaces instead after that. All right. So the point of what we're seeing right now is that there are objects that we can add and scale and multiply, not just the vectors in Rn. So oftentimes in mathematics, when you have sort of like a general phenomena that you see, let's see here, okay. All right, so when you have something like this, which seems rather broad, that you can apply to like many different objects of study, sometimes it helps to sort of abstract everything into like a general notion. And so that's kind of what we're doing with a general vector space. So we think of a general vector space as simply being like a prototypical object consisting of things that we can add and scale and multiply. And so one benefit of generalizing and abstracting certain notions in mathematics is it allows for sort of like a simultaneous study of all the different objects that satisfy those certain properties. And it can sometimes help to make your studying of these objects more efficient because you're focusing on just the essential details of what you're studying rather than focusing on like specific examples of the same thing over and over again, okay? All right, so a general vector space is essentially just a set or a collection of objects that can be added and multiplied by scalars. All right. So then, for instance, some examples of vector spaces, which we kind of already touched on. So Rn is sort of our prototypical example of a vector space. But as we talked about with matrices, that's also something that we can add and scale and multiply. So here I'll introduce some notation for each of these. So here M, and then subscript M by N. This will represent the vector space of all M by N matrices. You also have vector spaces consisting of functions, as I talked about earlier, because we can also add and scale and multiply functions. In this class, we're not going to look at that too much, but we are going to look, at least for some examples, at a space of polynomials. And so in particular, we're going to use this notation Pn to represent the space of all polynomials of degree that are less than or equal to n. Okay. And for us, most of the examples that we do are going to stick with just these three vector spaces. So that's all that I'm going to focus on and mention right now. Okay, now, I haven't given a super rigorous definition of a vector space, but if you check in your textbook or maybe just in your notes as well, you probably have a pretty long definition of a vector space. And there's a whole bunch of axioms or properties that have to be satisfied. So I'm not really going to list all of them, but I'll list some of them. So addition and scalar multiplication. And vector spaces. So they must satisfy various, I'll say they are natural properties. Right, such as, so for instance, addition of vectors should be commutative, so that u plus v should be v plus u. Should also be associative, so u plus v plus w should be the same as u plus v plus w. It should be distributive, so if you have a scalar times the sum, you should be able to distribute the scalar into the parentheses like that. And there were other axioms as well. I'm not going to list them all, but they're all pretty like natural properties that you come to expect from addition and scalar multiplication, all right? So I don't think I really need to mention them too much. And I'm not sure if you necessarily would even need to memorize all of them, at least not for this class, all right? So I'm not going to worry too much about it. What I do want to focus on, though, is talking about subspaces. Maybe before I begin that, I'll just ask if you guys had any questions about vector spaces in general. Okay. All right, so we'll spend most of our time on subspaces. So first, what is a subspace? So let's say we have a vector space, which I'll just denote by capital V. I'm gonna say no, or at least not really. So a vector space is just any collection of objects that you're able to add and scale and multiply. So I gave the examples of like Rn consists of these vectors that you can add and scale and multiply. But then I also introduced like the space of matrices. So they're all sort of related to each other in some sense, which I might be able to get into, and maybe 2 or 3 reviews from now. But I think it is good to think of them as being different from Rn. So I guess you don't necessarily want to think of matrices in the same way that you think of vectors in Rn per se. But they have a lot of similar properties when we focus on just the addition and the scalar multiplication. And so by inventing this notion of just a general vector space, anything that we define and prove for a general vector space would then be true in Rn. It will be true in the space of matrices. And it also by studying general vector spaces, it sort of allows you to study all the specific examples that we encounter kind of all at once by just focusing on a general notion rather than focusing on specific examples. I'm not sure if that answers your question or not. Okay. It's like a somewhat loose analogy, real quickly. It's like sort of like in calculus, how you guys learn to compute the derivative of any polynomial, right? So if I have the function 3x squared minus 4x plus 5, you can certainly tell me derivative will be 6x minus 4, assuming you guys haven't already forgotten your calculus. Okay, but in order to sort of understand how to compute the derivative of any polynomial, we gave these general rules on how to compute the derivative of a power of x, as well as these general rules for what to do when you have the derivative of a sum of 2 functions, where you can just take the derivative of each one and then add the results. And then we also gave a general rule for the derivative when you have a constant multiplying a function, how you're just able to factor the constant outside and then just differentiate the function and then multiply at the end. So it's having these general rules which allow us to then compute the derivative of any polynomial. So it's kind of similar. So we generalize all of the examples that we talked about up here into the notion of just a vector space. So then anything that we learn about vector spaces we'll be able to apply to all of our specific examples. Right? Just like how once we learn these rules, we can apply it to any specific polynomial and take its derivative. Okay? All right. All right. So now let's suppose that we just have some vector space, which I'm denoting by a capital V. So it could be Rn or a space of matrices or something else. So it doesn't really matter too much, but we've got a vector space capital V. All right, so a subset of V a subset W. So a subset W of V is a subspace of V. if W itself is a vector space. Okay, so that's kind of intuitive, perhaps. So subspace is just a vector space which is inside of another vector space. But in order to check whether a subset is a subspace, there are two conditions that you need to check. Okay. So the first condition that W needs to satisfy in order to be a subspace is that it has to be closed under addition. All right, so let's talk about what that means to be closed under addition. What it means is for any two vectors, W1 and W2, inside of this set W, their sum, W1 plus W2, must also be in W. Okay. So it's like if you take any two elements of W, you add them, you'll still be inside of W. So you can't like exit W by adding things together. So that's kind of why we say that's closed under addition when it satisfies this property. And then next, it also has to be closed under scalar multiplication. All right, so then what does it mean to be closed under scalar multiplication? It means that for any element little w of big W, and for any scalar C, if I multiply W by C, the result should also be inside the set W, okay? So if you have a subset of a vector space which is closed under addition, as well as closed under scalar multiplication, then it will be a subspace. And if it's not closed under addition or scalar multiplication, then it would not be a subspace. All right. And so I think the best way to kind of understand all of this is to look at a bunch of examples. So that's what I'm going to try and do right now. And so let's start with the first example over here. So I'll start by working with R3 as the vector space. And then I'm going to define a set W, which will consist of all vectors in R3, such that y is equal to x minus 3z. All right. So look at the set of all vectors whose y-coordinate is equal to the x-coordinate minus 3 times the z-coordinate. And then we want to ask, is this subset of R3 a subspace of R3? Okay. All right. So in order to check if something is a subspace, you have to check those two conditions, closure under addition and closure under scalar multiplication. So I'll start by checking the closure under addition first. So what we want to do here is pick any two elements of our set, W1 and W2. And what we want to show is that their sum, W1 plus W2, must also be in W. All right. Now, if you're trying to show that something is a subspace, so you're trying to show that it's closed under addition, so to be closed under addition, this property needs to hold for any two vectors inside of W. So it's not enough to choose specific elements of W with numbers. You have to keep it general to argue that it works for any two elements of W. So what I'm going to do here is I'm going to use letters for the components of W1 and W2. I don't want to use specific numbers because that won't be able to prove that it's closed under addition. All right, so I've got my two vectors, W1, W2. They're vectors in R3, which is why they have three components. And because they are in W, that means that each of them will satisfy this condition. So that means, although we don't know what these numbers are, but we do know that y1 will be equal to x1 minus 3z1, and that likewise y2 should equal x2 minus 3z2. So we've got two vectors in W, so they satisfy these conditions. What we want to do is now add them and check to see if the sum is also inside of W. So first things first is I'll go ahead and add them together. All right, so addition is just the usual component-wise. So it's x1 plus x2, y1 plus y2, and z1 plus z2. Okay, so then we have the x, y, and z coordinates of the sum. And then to check if the sum is inside of our set, we need to check if its x, y, and z coordinates satisfy this condition. So what I'm going to do is I'm going to take the y-coordinate, y1 plus y2, and I want to see if it will be equal to x minus 3 times z. Now to do this, I want to make sure that I'm using these properties here. I'm using the fact that W1 and W2 are already inside of W. So because of that, we can say that Y1 was equal to X1 minus 3Z1. And we can say that Y2 was equal to X2 minus 3Z2. Now what I'm going to do here is I'm just going to rearrange these terms a little bit. I'm going to group together the x1 plus x2. I'm going to group together the minus 3z1 minus 3z2. And I'm going to factor out the minus 3 as well. So it'll be minus 3 times z1 plus z2. Okay, so then here what we see is that the y-coordinate of the sum is indeed equal to the x-coordinate of the sum, and then minus 3 times the z-coordinate of the sum. So in other words, the sum satisfies, let's see here, okay. So the sum satisfies this defining condition, and so therefore it is within the set W. And so we can say therefore, the sum W1 plus W2 is in fact an element of W. So what this shows is that if you take any two vectors in W, their sum is ultimately also a vector in W as well. So because of that, we can conclude that W is closed under addition. All right. Now that's not enough to conclude that W is a subspace. So to prove that it's a subspace, we also need to show that it is closed under scalar multiplication. So before I do that next, I'll just pause briefly and ask if you guys had any questions so far about how I showed in this example that it was closed under addition. All right, so in that case, we'll take a look at the scalar multiplication next. Yes, so if the closure under addition already wasn't satisfied, then you could stop and say that it was not a subspace, and you would not need to check the scalar multiplication next. Okay, so let's see here, closure under scalar multiplication. So let me review quickly what this meant. So it's if you have an element of W, and then if you have a scalar, which we'll call C, then when you scalar multiply C times W, this result should also be in W. So let's do what we did before. I'll start with a generic element of W. So that means that W would be a vector with 3 components, and its y-coordinate will be the x-coordinate minus 3 times the z-coordinate. Okay. So then, assuming we have a vector satisfying that condition, if we multiply this vector by a scalar now, okay, so we know that that would just multiply the scalar to each component. Oops. Yeah. So then that gives us like a new x-coordinate, a new y-coordinate, and a new z-coordinate for the vector CW. So now if I take its y-coordinate, CY, I want to check if it's equal to the x-coordinate minus 3 times the z-coordinate. And to do that, I want to make sure that I use my assumption that W satisfies this property. So using this assumption, we can replace y with x minus 3z. Okay. And then if we distribute the c, we're going to get cx minus 3 times cz. And then when we rewrite it like this, we see that the y-coordinate is in fact equal to the x-coordinate minus 3 times the z-coordinate. Okay? So that means vector CW also satisfies this property. And so therefore it is also an element of W. So this shows that take any vector in W, multiply it by any scalar, the result is in W. So that shows that W is closed under scalar multiplication. Okay. So then finally, because it's closed under addition and scalar multiplication, we can conclude that W is in fact a subspace. All right, so that would conclude the first example. All right, so then any questions about anything so far? All right. So I'm going to be doing some more examples. Yeah, one moment. Okay. Okay, all right. All right. So let's look at another example. Let's look at an example where you would not have a subspace. So I'll continue working in R3 for the moment. I'm going to define another set, W, which will consist of all vectors in R3, such that x plus y is equal to 2. All right. So let's try to check if this subset of R3 is a subspace. All right. So what I'm going to do right now is I'm going to look at the closure under addition. All right, so suppose we've got two vectors in W. And again, I'll write out W1 as x1, y1, z1. And then W2 can be x2, y2, and z2. And so being elements of W, that means they have to satisfy this condition. So their x coordinates plus their y coordinates must equal 2. Now, if I were to add my two vectors, I would get x1 plus x2, y1 plus y2, and then z1 plus z2. Okay, so then we've got the x, y, and z components of the sum. So now we want to check if the sum will satisfy this condition or not. So if I did x coordinate and then plus the y coordinate, all right. If we use these two assumptions that we had on the vectors w1 and w2, okay, so x1 plus y1 will equal 2, and then x2 plus y2 will equal another 2. So here we see that x plus the y coordinate would actually equal 4, not equal to 2 though. So because it did not satisfy this condition, you had x plus y was equal to 4, not equal to 2. So then that would prove that the closure under addition did not work. So W1 plus W2 is actually not inside of W. So therefore, it's not closed under addition, and therefore it's not a subspace. All right, and so there's no need to check the scalar multiplication in this example because we can already conclude that it is not a subspace, okay? And so any questions about that? Okay. All right, let's look at one more example in R3 for the moment. So let's suppose that this time W is the set of all vectors in R3. Such that X, Y, and Z are greater than or equal to 0. So if you will, W is what people usually call the first octant in R3. So like whenever people draw a picture of R3, they usually only draw the first octant. All right. So we want to ask if this would be a subspace or not. Yeah, so if closure under addition checks out, you should still check closure under scalar multiplication to see if it's a subspace or not. So this one is actually kind of a good example of that. All right, so if you have two vectors, and if we assume that all of their components are non-negative, when you add them up, the components are also going to be non-negative. So x is greater than or equal to 0 because x1 and x2 were greater than or equal to 0. So the sum should also be. Same for y and z. So this would show that it is closed under addition. All right, but then if you also want to check if it's closed under scalar multiplication, so imagine if we let's just take the vector W1. So again, all of its coordinates are non-negative. But what happens when we multiply it by a scalar? Whoops. So then are the x, y, and z components here necessarily going to be non-negative? Okay, so what do you guys think? If x1, y1, and z1 are greater than or equal to 0, Is it necessarily the case that after multiplying by a scalar c, that everything would remain non-negative? Exactly, yeah. So remember that for checking a scalar under multiplication, you have to consider all possible scalars. That means you would have to consider negative scalars here. Oh, let me. Okay, yeah, my computer lags a little bit, so I apologize for that. Okay, but yeah, so the answer is no, not necessarily. If C is negative, then these conditions would not necessarily be satisfied. Sometimes when you're trying to show that something does not work, I find it useful to provide a specific counterexample. So for instance, I can take a vector like maybe 1, 2, 3. So this would certainly be a vector in W because all of its components are positive. But when we multiply this vector by the scalar -1, all the components become negative. And so that means it's no longer inside of W. So therefore, you can see that's not closed under scalar multiplication. So even though this example, it was closed under addition, it's not closed under scalar multiplication. And so ultimately, it's actually still not going to be a subspace then, okay? All right. So any questions about that? All right. Okay, so I'll quickly say a couple of things about subspaces in Rn, and then I'll do examples involving matrices and polynomials. So first, regarding what are the subspaces of R2? So it's possible to list all of the subspaces that are inside of R2. All right, so first things first, it's good to note that every vector space is going to be a subspace of itself. So in other words, R2 is a subspace of R2. Now similarly, if you take the set just consisting of the zero vector, that will always be a subspace as well. It's closed under addition because 0 plus 0 is always 0. And it's closed under scalar multiplication because if you multiply 0 by a scalar, it's just going to be 0, okay? So you always have at least these two subspaces for any vector space, the zero vector and itself. Now, in addition, for R2, any line passing through the origin is also going to be a subspace of R2. So maybe I can just give a quick illustration of that right now. So if you draw a line in R2, so maybe first imagine if you take two vectors along this line. Well, when you add these two vectors up, you're still going to get a vector which lies on the line. Similarly, if you take any vector on a line passing through the origin, and you multiply it by a scalar. So as you guys recall, when you multiply a vector by a scalar, whether it's positive or negative, the result will still lie along the same line. Okay. So therefore, you can kind of see just by this illustration how a line through the origin would be closed under addition, as well as scalar multiplication. So then, aside from these examples here, there are no other subspaces within R2. So in other words, these are actually the only subspaces within R2. So any other subset of R2, which is not aligned to the origin itself, or R2 itself, any other subset would not be a subspace. So either closure under addition would fail, or closure under scalar multiplication would fail. Okay. Now you can do something similar for R3. So I'm just going to quickly mention that one. Okay, so again, the origin by itself is going to be a subspace, as well as R3 itself, that would also be a subspace. Any line through the origin will also be a subspace of R3. Now likewise, any plane passing through the origin in R3 will also be a subspace of R3. And then it turns out that this is a complete list of all the subspaces in R3. So that again, any other subset of R3 not on this list would not be a subspace. So you can sort of generalize that to any Rn. So R4 would not be a subspace of R3, that's correct. Because R4 is not even a subset of R3 to begin with. So you have to have a subset first within the vector space to be a subspace of that vector space. Okay. All right. Now I'll say a couple more things, some more facts about subspaces, which are good to know. And then I'll do some more examples. So you have to give me a couple of seconds because my computer is slightly frozen again at the moment. So I just need to wait for it to sort of unfreeze. Okay, there you go, finally. Okay. Okay, so we've learned that a subspace has to be closed under addition and scalar multiplication. So I want to point out two consequences of that. First is that any subspace has to contain the zero vector. This is because this is a consequence of the closure under scalar multiplication. So because of that property of being closed under scalar multiplication, if you take any vector inside your subspace, any scalar multiple of that vector must also be in the subspace. So in particular, when you multiply by the scalar 0, the result, which is the 0 vector, must be in the subspace. And that's how you can see that any subspace must contain the origin. So the reason why this is useful is because if you see a problem and you notice immediately that the 0 vector is not inside of that set, then you can immediately say that it is not a subspace because it does not contain the 0 vector. Yeah, so that's a good one where previously we had the example x plus y equals 2. So the 0 vector would not satisfy that condition. So you could argue, therefore, since the 0 vector is not in that set, that's another reason for why it would not have been a subspace. Okay. Now, the other fact I want to point out is that another way that you can check whether you have a subspace or not, you can see that a subset is a subspace if and only if it is closed under linear combinations. Because if you remember what a linear combination was just a combination of scalar multiplication and vector addition. So if you have a subspace, it's already closed under scalar multiplication and addition, so it's going to be closed under linear combinations. And vice versa, if it's closed under linear combinations, since that includes scalar multiplication and addition, it would therefore be closed under both, okay? So one consequence of this is that if you recall the definition of span, which we defined for Rn, but which we can also define for a general vector space. So I'll write down the definition again, the span of some collection of vectors, let's say v1 through vk, is the set of all linear combinations of these vectors. So I gave this definition earlier for vectors in Rn, but the same definition holds really for any general vector space. And the span of any collection of vectors is always going to be a subspace. Okay. Reason being because since it contains all the linear combinations, it's sort of by definition going to be closed under linear combinations because it contains all of them. And so therefore the span of any collection is always a subspace, all right? So that's a useful fact to know. All right, so now with the time I have remaining, I'm gonna kind of quickly go over subspaces of matrices. I'll focus on subspaces of n by n symmetric matrices, so square matrices. So I'll just look at some examples and I'll try to do them a little bit quickly since I'm running short on time. But let's start by looking at the space of, or the set, which I'll call S n by n. So this would be the subset of all n by n matrices, consisting of all the symmetric matrices. So we want to ask, is this guy a subspace? So to check this, we'd want to check the closure under addition and the closure under scalar multiplication. Now, before I get to that, let's just quickly recall. What does it mean for a matrix to be symmetric? So remember, a matrix A is symmetric if and only if its transpose is equal to itself. So just kind of quickly, if you remember in my examples, how there is always a condition that needed to be satisfied to be within the set. So for instance, like the x plus y equals 2 type of condition. Yeah, so here for a symmetric matrix, the condition that needs to be satisfied is that A transpose must equal A. So let's try to check the closure under addition right now. Okay, so how does closure under addition work? So let's recall. It says if I have two elements of my set, then their sum should also be in the set. So in this context, for this example, it means if I have two symmetric matrices, is their sum also going to be symmetric? So let's check that. So assuming A and B are symmetric, meaning A transpose must equal A and B transpose must equal B, we want to check if their sum is going to be symmetric. So what happens when we transpose A plus B? You guys might remember that transpose, you can distribute it when you have a sum. So it's the same as A transpose plus B transpose. And since A and B are symmetric, that means that this is equal to A plus B. So therefore, it looks like when you transpose A plus B, it does return A plus B. So that would prove that the sum is in fact symmetric. Yeah. So therefore, the sum of two symmetric matrices is symmetric. That means it is closed under addition. If I check the scalar multiplication next, okay, so imagine again you got a symmetric matrix. So now what happens when you multiply that matrix by a scalar? So the question is this matrix symmetric? So we can check that by taking CA and checking if its transpose will be equal to itself. Okay. So if you use a property of transpose, remember that if you're multiplying by a scalar, you can just pull it out to the front. And then since we're assuming A is symmetric, that's just the same as C times A. So therefore, we see that the transpose of CA is itself, meaning that CA is a symmetric matrix if A is symmetric. So therefore, it's also closed under scalar multiplication. So because it's closed under addition and scalar multiplication, we can conclude that the space or the set of n by n symmetric matrices, it is going to be a subspace of the space of all n by n symmetric matrices. Okay. Any questions about that? So quickly, some other examples. If you take all n by n upper triangular matrices, this is also a subspace of the space of all n by n matrices. So when you add two upper triangular matrices, the result is upper triangular. So it's closed under addition. If you take an upper triangular matrix and you multiply it by a scalar, the result will still be upper triangular. So therefore, it's also closed under scalar multiplication, okay? Same for n by n lower triangular matrices. N by n diagonal matrices. I don't think you guys have really talked about it yet, but I'll just kind of mention it. If you look at n by n skew symmetric matrices, or sometimes people say anti-symmetric instead. And just kind of real quickly on that, what is a skew symmetric matrix? It's one whose transpose is equal to the negative of itself, okay? So these are some examples of subspaces of the space of n by n matrices. So I'll go on a little bit longer, but of course you guys are free to leave at any time. The recording will be up later for you guys if you need to leave now, okay? I'll just mention a little bit more real quickly. I want to look at just a few examples of subsets which are not subspaces. So if we consider all n by n invertible matrices, this would not be a subspace of n by n. So the reason why it's not a subspace, the simplest reason is that it would not contain the zero vector. The zero vector being the n by n zero matrix, okay? Likewise, because the zero matrix is not invertible, so that's why. But likewise, if you look at all n by n non-invertible matrices, it's also not a subspace of n by n. One reason for this is that it's not closed under addition, for instance. And then just to give a small example of that, so here's an example of two matrices which are not invertible. So they're not invertible, and one way we can tell is because it has a row and a column of zeros. But you notice that it adds up to be the identity matrix, which is invertible. So when you add two non-invertible matrices, it's possible that the sum is invertible, so therefore it's not closed under addition. And finally, I do want to also quickly highlight some examples with polynomials. So if you remember how we talked about Pn, representing the space of polynomials of degree less than or equal to n. So first, it's worth noting is that if I consider the set of polynomials of degree not less than or equal to n, but if I did exactly equal to n, this would not be a subspace. Of Pn. Reason being is because it does not contain the zero vector, for instance. Maybe we should assume n is larger than, well, no, it's okay. Yeah, okay. Because it does not contain the zero vector, which in this case would be a zero polynomial, which for reference would just be the polynomial, all of whose coefficients are zero. Okay. And so just to be clear about this example is that for the degree to be exactly n, that means that the coefficient of x to the n cannot be equal to 0. So it has to have an x to the n term in it, okay? All right. Then, so some examples of some subspaces real quickly. Okay, so let's take, specifically, let's just work with polynomials of degree less than or equal to 2. So that would be any polynomial of this form. Now, if I take W to be the set of all polynomials in P2, such that P evaluated at 5 is equal to, say, 0. And then we want to ask, is this a subspace? Now that I think about it, I guess it doesn't have to be P2. Any Pn would work, but that's fine. So let's just maybe quickly try to check the closure properties. So let's suppose we had two polynomials, which I'll call P and Q, inside of the set W, meaning that P at 5 would equal 0, as well as Q at 5. Okay, so if we think about what happens when we add our two polynomials together. So if we add the polynomials and then we try to evaluate at 5, okay, so this should equal P of 5 plus Q of 5, because that's how we add polynomials together. That's how we add functions together in general. All right, but assuming that P and Q were in W, this would be equal to 0 plus 0. And so therefore, we do have that the sum evaluated at 5 also equals 0. So it would be closed under addition. Then quickly checking the scalar multiplication. So let's just take P of X as before. So that P of 5 equals 0. So consider what happens when you multiply by a scalar. Okay, so we know that when you multiply by a scalar, you can just factor it out to the front. And then since P of 5 is equal to 0, that means this is also equal to 0. So even after multiplying by a scalar, when we evaluate at 5 equals 0, so it's also closed under scalar multiplication. So therefore, it's closed under both addition and scalar multiplication. So it is a subspace. Okay. And then just lastly, if I were to make a small modification to this problem, let's say instead of equal to 0, if it were equal to any other number, for instance, if it were equal to 1, whoa, okay. If I change the number 0 to any other number, it would no longer be a subspace. So for instance, you can check closure under addition. And when you check closure under addition, the sum, when you evaluate at 5, it'll equal to 2. So no longer equal to 1, so it would not be closed under addition. You can also argue it would not contain the 0 polynomial, but I just wanted to give that quick example. If I change the number 0 to any other number, it would no longer work. Okay. So at that point, I'll end my review now.